Alright, now that that power switch has been repaired, let's move on to something else I mentioned, which was making this safer and more efficient by improving the circuit for this series filament arrangement. Okay, simple way to make this safer is to add a fuse. Here's the schematic. We got the AC coming in here, and one side goes to the filaments, the other goes to the rectifier, and here's the switch. I'd say the easiest place to add a fuse would be like right in here. According to the documents, this radio draws about 60 watts. So a simple way to think about that is watts is voltage times current. So if you got 125 volts AC at the outlet and it's drawing 1 amp, that's 120 watts. So if this is 60 watts, that's about half an amp. Now if you put a 1/2 amp fuse in here, it'll probably blow as soon as you turn the radio on, because when these filaments are cold, they have lower resistance and they draw a little bit more current. You'll see that when you turn the radio on, that the pilot light surges bright for a little while and it dims down. That's these filaments heating up, and hot wire has more resistance, so less current flows through it. So you'd either want to use a higher amperage fuse or maybe use a slow blow fuse. 3/4 amp fast blow might do it. I'd probably go with a 1 amp. I think I've got some of those on hand. Now, as far as installing it, one package calls for drilling a hole in the chassis, and you'd mount it on that, and then it'd have a screw cap. So it's convenient if you ever need to replace the fuse. You can just unscrew that, pop in a new fuse, and so on. But that means you have to damage or alter the cabinet, which I'm not crazy about. Plus, if you've done a good job restoring a radio, you shouldn't really be blowing a whole lot of fuses very often. In fact, I don't think I've ever blown a fuse in any TV or radio that I've restored. So what I am going to do is use some pigtail fuses, which is a small fuse that actually has a lead coming out of either end. It looks kind of like a capacitor. And I just tuck that in discreetly somewhere into the chassis. So on the off chance that the fuse does blow, you would have to pull the chassis and get in there and unsolder it and put a new fuse in. But I like to go with keeping the original appearance as much as possible, so that's what I'm going to do. Now, as far as improving the circuit, well, here I've drawn a simplified version of it. If you add up all the tube filaments together, you get 68 volts. There's a 25 Z6, and the 25 means it draws, or the filament takes 25 volts. 25 A6, and then 3 6-volt tubes. So 25, 50, and then plus 18, you get 68. Well, I got 120 volts more or less coming out of my outlets. Back when this was designed, it was probably 115. Line voltages have increased a bit since the 30s in this country. So you got to make up for that somewhere, or the tubes are just going to blow out. So what they did is they put in 2 power resistors. 130 here, and then there's a 30 with a pilot light across it. The reason they did that is if you just had this in series with the tubes, the lamp would burn out. So they had to put a series resistor, or sorry, a resistor in parallel with it to drop that down. Now I'd like to replace this, but since it's working and it kind of works in conjunction with this light, I'm going to leave that alone. So I'm just going to try to improve this. Now you might be thinking, there might be other versions of these tubes that have higher filament voltages, and there are. Like, for instance, I've got actually a 25L6 for the output. Well, there's commonly available a 50L6. And I think there's a 35Z6, and I think there's a 12K7, maybe a 12Q7. So if you increased all of these, you probably could get pretty close to 120. Problem is, they won't draw the same amount of current. For example, if you look up the data for all of these tubes, they all draw 0.3 amps on the filament. Now if I left those the same and just put a 50L6 in there, there's going to be a problem, because a 50L6 has a filament current of 0.15 amps. Because these are all in series, you need to have the same amount of current going through all the tubes. And if you throw a 0.15 amp tube in there, that's going to cut down the current to the other tubes. It's going to mess everything up. So you really can't do that. Unless maybe you could find a 0.15 amp version of all the tubes that added up to 120, but I just don't think that's possible in this case. But there are a couple very easy circuit variations you can do to improve this. One is, instead of that resistor, you put a diode in a resistor. A diode will right off the bat cut about half the voltage going to the tubes, because you got your sine wave coming in, and this diode will kill all the negative portion. So it cuts the power more or less in half of going to the tube filaments. And it's also a good idea to put a series resistor in here, because when you turn this on, like I mentioned, the filaments are cold and there's a bit of a current surge. So it's a really good idea to have a resistor in here to help limit that a little bit. Now, more interestingly, there's another variation that only takes a single bipolar capacitor, and this will dissipate no heat. Whereas with the series resistor and the diode, this will drop a bit of heat. Far less than the 11.7 watts this would dissipate, because wattage is I squared times R. So we've got our 0.3 amps going through the filaments, which will also go through this resistor. So 0.3 squared times 130 is almost 12 watts. That's why that side of the radio gets so hot. This will be far less. We'll calculate in a minute exactly what this would come out to. But this dissipates no heat. I found this out by a very helpful tip I got at the Video Camera Antique Radio Forum, and I was given a link to this awesome website. I hope you can read that off. I'll put it in the YouTube video description as well. So the first example they give here is to calculate the resistance dropper if you just want to use a single resistor. Well, we already know that it's 130 ohms in this case. And then here they show using a diode and a dropper resistor. This is a British site, so they talk about valve heaters, valve vacuum tubes, same thing. AC mains, that's your wall outlet. And then below that, they show that. Can't get any simpler than that, and it works amazingly well. Formula's not so simple though. To figure out the values you need for these various things, you get into stuff like phase relationships and so on. But after reading through all this theory and so on, they give you a link to a spreadsheet that will do the calculations for you. I have downloaded it, and I've got it up on my other screen. I believe this is open source, and he's asking if you find this useful to donate a little money, so please do that. If you go to this site and you find this and find this useful and make use of it, throw them a few bucks, why not? Okay, so here is what that spreadsheet actually comes up as. So I've already plugged in my numbers: 120 volts, 60 hertz. We got our heater voltage at 68 volts, heater current 0.3 amps. The surge limiter drop, that only is in with the capacitive circuit. You could go with something as simple as this, but they suggest that you add a resistor in there. Like I'd mentioned before, to limit that current when you first turn it on, so you don't fry the tube filaments. So they suggest putting a nominal 10 volt surge limit drop there. Well, if you plug all that in, here is if you just had a series resistor. Now mine's 160 ohms, this is 173. That's because when this radio was designed, most likely they had 115 there, not 120. So I need to burn off a little bit more. But you can see it's wasting about 16 watts there if you just use a series resistor drop. Resistor with a diode down to 5 watts. And with the capacitor, only 3 watts. and it would be 0 except for that resistor that's put in there for the surge limiter. Now, the only problem with this is I have very few large non-polarized caps on hand, and I certainly don't have one that's 8.7 microfarad. I might have a 10 lying around, but I doubt that. But I certainly have a diode and a 56 ohm resistor, so I'm going to give that a try first and see how that goes. Next time I place an order for capacitors, I'll try ordering something that's pretty close to that. Closest standard value I think would either be 8.2 and maybe a 9.1. 10 might be a little bit too high, but if I go with 10 and then play with that resistor of 33 ohms, it might work out okay. Okay, now before anybody posts a comment, yes, I did make a mistake. I had put in 68 volts for the heater voltage and 128 volts input. I kind of forgot about this part over here. So what I did is I calculated the voltage drop over here, and it comes to about 13 volts. And then I just lumped it in with that, so that actually is about 81 volts over here, and then 120 input. So if I do that, I actually get a dropper resistor with a diode of 13 ohms at a little over a watt. Also makes the dropper capacitor just about 10 microfarad, which is certainly a standard value. So, it also occurred to me that's pretty easy to make up, because I can take two 22 microfarads and connect them back to back and make it a non-polarized capacitor. So, next up, I'm going to try out both of these techniques and see how they work out. First up, the diode. Here's my simplified schematic again. So, AC power. I'm going to use a 1N4007 silicon resistor. That's very common, very handy resistor to have. Handles 1 amp, 1000 volts. Great for replacing selenium rectifiers and old equipment. Got my 13 ohm resistor here. And then here's my lumped tube filament and that light bulb. Then we got a switch, and then there's my 1 amp fuse I'm going to put in there. Here are the components to build the diode resistor variation. This is a 1N4007 diode. Didn't have a 13 ohm 2-watt resistor on hand, but I do have a 47 ohm and a 20 ohm. I'll put them in parallel. That's 14 ohms, which is pretty close. And here's that pigtail fuse I was referring to, where you can solder it in directly under the fuse leads. Now, as for where to wire this stuff in, well, here's my AC line. Here's the one going to the switch where I want to put the fuse in. And here's the other end. And here's that 130 ohm resistor in here. Now, remember, this does go to some other stuff. So in addition to the resistor, there's a wire going down in here and a capacitor. So I want to leave this end attached, but I'm going to disconnect the one wire going over here and move it closer and put my diode and resistor in over here. Okay, I installed a fuse down in here right off of the AC switch. And here is my diode and 2 resistors. Of course, I wouldn't really leave it like this when I'm done. I just want to leave these exposed so I can see how hot they get. Radio's plugged in. So, here we go. A pilot lights seem to come on a lot brighter at first, but it seems to be the normal brightness level. And that was kind of my one concern with using a lot less resistance in a silicon diode. I thought that there might be a lot more of a surge current, but I bet the capacitor circuit will take care of that. In fact, that's what was recommended to me online, is that the capacitor circuit is a lot nicer surge characteristic. it certainly worked. That's the important thing. Let's see that again when it starts up. Turn the lights off this time, the camera lights. See how much of a surge there is. Well, it is a little bit of a harsh startup. I'll let this run a little while. I'll put the camera down so I'll just run a while and let's see how hot this area gets. Well, it seems pretty cool just with my hand hovering over it. Okay, it's been about 15 minutes, so let's see. Well, it's warm, but yeah, it's really not that warm at all. It was always, going by the calculations, it was only going to dissipate a little over 1 watt anyways, and that's right about what it is. So, side of the radio is cold now, and this is not that warm, but also does as was calculated. It reduces that power consumption from over 10 watts down to about 1 watt. Alright, finally we have the capacitor circuit. I went a bit overboard with some of the component ratings just because they were handy. These are 450 volt caps, which are a bit more than I would really need. And this is like a 30 watt resistor, which I don't need, but it was the right resistance value, so that's fine. So what I did is, since I don't have a non-polarized 10 microfarad, I took two 22 microfarads back to back, kind of the negative leads together, but I think you could do the positive together, it doesn't really matter, as long as the same polarity go together, and then go to the opposite sides. So what this does is it makes it not only non-polarized, so you can run AC through it, but it cuts the capacitance in half. So this is actually only about 11 microfarads. Then there's 120, or actually I used 150K resistor across it, which is really just there to bleed off the charge quickly when you turn the radio off. And then finally there's this 33 ohm resistor to act as a bit of a surge protection when you turn the radio on. So let's give it a try. Turn the lights off again so you can see what the surge is like. And here we go. Huh, it seemed dimmer when it starts up, which is good. I don't want that bright flash like I was getting before. Well, it seems to work just fine. I'll let this run for a while and see how warm it gets. Okay, it's been running for a while, and this resistor is getting kind of toasty, and I thought about it, and of course it is, because we still have the 0.3 amps running through this, and it's I squared R, and 33 ohms is even more than 13, so this is actually going to get even hotter than that is, and that's why there was a 3 watt rating on it. So in reality, this is actually dissipating more heat than that. So what I'm going to try doing is dropping this resistor down, because it says that that resistor is really there to limit the surge when you turn the radio on. But from what I observed, there was no surge current at all when this was turned on. So I think I can go quite a bit lower on that. So I'm going to try going to about 4.5 or 4.7 ohms, which is about a third of what I had on that. And let's see how that goes. Well, I couldn't find a 4.7, but I did find a 6.8, and that should be about half the dissipation that I got with the diode circuit. So let's give it a try and see what kind of surge we get when I turn it on. Here goes. Huh. Didn't notice any surge at all, which is just great. I'll let that run for a while and see how hot that resistor gets. And the final thing I really want to do is hook up an AC voltmeter and check the voltage drop across here and make sure it really is around 81 volts AC, because I don't want to be putting too much voltage across those tube filaments. If it's a little bit less, that's okay, because it'll just extend the life of the receiver. As long as the volume is sufficient, there's no problem with running the tubes a little bit cooler. Okay, it's been running about 10 minutes now, and the resistor, it's warm, but certainly about what I expected. It just seems to be less than a watt. I can touch it, and it's not horribly hot. So, certainly less power dissipation than the other circuits. Again, it's I squared R, so whatever 0.3 squared times 6.8 ohms is, that's how much power is being dissipated. As for the voltage, 79 volts is being dropped across here, so a little bit less than was calculated, which is great. One thing I want to check is, I've been assuming that I have 120 volts AC coming in. Let's actually check that with a meter just to make sure that I'm not way off with anything. I'm 20.9, so hey, everything works out just fine. So I am going to go with this circuit because it's working fine. It does exactly what I was hoping it would do. My problem is these capacitors are overkill, and I did buy them for another project. These are kind of expensive. So I am going to pick up a proper 10 microfarad non-polarized cap the next time I place an order, which may be a little bit of maybe a little while. So I'm going to remove this and wire this back in, but once I do get a proper cap, I think I'll do a follow-up video to show you how the final thing works. But for now, hey, I think I gave you a lot of food for thought about what you can do to improve the performance and the safety of series wired AC radio. That's all for now.